I'm going to talk to you today about soft-wired neuron brains. This is a personal project I've been working on and off for the last 6 months. So what's the inspiration for this work? Neurons are responsible for all thought, at least we think. Models can be used to learn things. Neurons and brains are developed via evolution. Therefore, an evolutionary model of neurons could help us understand thought. Well, eventually, in the meantime, simple neuron circuits have been identified that perform simple tasks. For example, here's the tap withdrawal neuron circuit schematic for C. elegans. This is basically if you touch a C. elegans, how it actually, the mechanism that actually causes it to retract. So the idea with the soft-wired neuron brains, the plan is we create an evolvable brain model with a modular neuron description, and then we evolve these brains under various conditions to see if they generate biological-like neural circuits. We tweak the neuron descriptions and problems in order to create more biological-like and more complex, i.e. smarter brains. And then we learn stuff about brains, and we make smart computers, and we advance humanity. So from an overview, what these soft-wired neuron brains are going to be is a collection of interconnected neurons. The neuron networks should exhibit small world qualities. The neuron connections must be able to translate smoothly over evolutionary time. Neurons should be capable of complex logic, and there must be a method for input and output. So let's talk about what a neuron in this model that I'm developing looks like. Neurons take some inputs from other neuron outputs. They process these inputs through some logic, and then they output a result. The logic within a neuron can be any logic that works with a fixed number of inputs. So these can be like a traditional threshold logic in a neural network. They can be Boolean logic like you'd find in a Markov brain. They can be math like you'd find in a GP tree, any sort of fixed number of input logic. But real neuron inputs are more complex than this. So we're going to allow the inputs to have inputs. And this will generate dendritic branches. Of course, at that point, we should allow these dendritic branches to have their own logic. So the dendritic branch logic must be able to handle any number of inputs. This can do accumulator logic, averaging, value detectors, sign detectors, other things, other sorts of logic like that. So here's the schematic that I've been working with. You can see the branch structure here. In addition to the inputs and the branch logic, there's a branch weight on each branch. It flows into the neuron logic. This then flows to an output. The output is immediately accessible to other neurons. We update all neurons in the brain first, and then we move all of the outputs to prior output. That way, the brain effectively updates in parallel. You'll notice a few other features. There is this input neuron switch. There's an XY location. And then there are these connection tags and strength tags on the outputs and on each of the dendritic branches. There's a connection tag and a strength tag. While I'm on this slide, in the results I'm going to show in a second, all of the dendritic logic is just averaging the branch inputs, and all of the neuron logic is based on a thresholding gate. It accumulates inputs with a decay. If the input exceeds the threshold, they fire. So how does input and output work? Inputs are delivered to the brain using input neurons like this in1 here. These input neurons have no branches and no logic. They only have output tags and location. Normal neurons can connect to the input neurons just like any other neuron, and then the brain outputs they have a location and they just connect to the closest neuron. And how do we make the brain? To make the brain, all neurons and outputs are positioned. The connection tags and distances are used to create connections between neurons. Strength tags are used to determine the strength of each connection, and outputs are connected to the nearest neuron. So how do they evolve? So I evolved this on 3 different worlds. I'm using MABE, so it's trivial to do this. The first one is NBAC. Basically, a stream of bits are fed to the agent, and we ask it to regurgitate what those bits were. It's a memory task. It performs fine, as well as Markov brains and ANNs. We ran it on Berry World. This is a navigation and value judgment task. They perform better than ANNs and worse than Markov brains. And then I took the path following task from Insemo et al. 2020, I simplified it a little bit. Funny, there's a concurrent talk in the other session right now that's using this same world. And this is a navigation, learning, and memory task, and it performed as well as an ANN, but significantly worse than a Markov brain. These are some of the circuitry diagrams. This is for NBAC. Interesting thing here is you can actually see the data flow. So the data comes in here, and then it passes through these neurons, and this is the first output, and then on the next output, and the next one. So you can actually see that the data flows through the connections in this brain. Here's a path following brain. I have no idea what the logic is here. Here are some berry brains at 2 different points in evolution. Note that there's some unconnected neurons here. This is some of the paths that are generated in the berry brain. You can see that the complexity increased over time on the strategies that they're developing. So for future plans, more logic types, local memory for the neurons beyond just the local thresholding information, some fire together, wire together, Hebbian type learning, neuromodulators, pre-processing so I can ignore unconnected neurons, and more. And then I just want to thank Heather Easton, who's just been a great teacher for years, getting me interested in neurobiology, and Chris Reeves, who's I think senior now, undergrad, who I had a lot of conversations with about this model last year. So that is all. I'll take any questions.
Great talk. Thank you, Cliff. So the chat and hand raising is open for questions. We've got time for a couple.
Where did sorry, I'm looking for the stop share. There we go. Okay.
I've got a question. I'm sorry if you said this and I missed it because I was doing moderating stuff. Have you compared like how wire brains perform to some of the other brain types in MABE yet? And if
Well,
so,
I mean, so that, yeah, that was the, I did look at, I'll just share really quick. I went really fast, I know. So that was this. So this is looking on these 3 tasks where NBAC is a pure memory task.
Right,
Berry world is navigation and value judgment, and path following is memory, associative learning, and navigation. And it's holding its own, considering that I haven't developed any significant logic models for it. I think it's actually doing pretty well. Like it needs significantly better types of gates. How many neurons can I realistically work with? That is a fine question. I don't know. I have had brains with upwards of 90 to 100. They do start to run slower. And certainly being able to optimize, like being able to do that short circuiting so I don't run unconnected neurons will really help with that. But also I think I can probably design this in a smarter way to allow for parallel processing somehow. But I guess on the other hand from that, a lot of the neural circuits that have been published, they're on the order of single digit to, you know, maybe 10 or 20 neurons in that circuit. So what I'm really hoping is that this system will be able to evolve those kinds of circuits.